Hello, so if you remember in the last video we put lots and lots of ideas together and we had a setup look like this, and we essentially found that the gradient of a curve, of any curve, can be given by this formula, and this formula is sometimes called first principles. Okay, and it's a really important formula in the calculus world. Now this dy over dx, the way to say that is dy by dx, okay, just in case you're unsure. Whenever you see that, you just say dy by dx, dy by dx, okay? Right, so now I'm going to give you an example. So let's suppose we have y is some function of x, and let's suppose that function is x squared. Now I'm just going to very quickly talk to you about what equals actually means, because it's appropriate here. We've been using equals for years and years and years. Equals means is equal to, so one thing is equal to another. So here we've got y is equal to some function of x. We can also think about it as y being the same as a function of x. There's a few ways. It's a bit like looking at a coin. Right? It's the same object, but if you look at it from a different angle, you'll see a different view. Like you look at the head side or you look at the tail side. So, I mean, I could write, for example, x is 3. That literally means that they're the same thing. X is 3. But here, what I can think of equals as is whenever I see a y, that means the same as f of x. So I've got y is equal to f of x. Y and f of x have the same meaning. So whenever I see an f of x, I can just write y. Or whenever I see a y, I can write f of x. They literally have the same meaning. So here, I can see an f of x is equal to x squared. Well, I can replace that with y is equal to x squared. So I've replaced the f of x with y. They're interchangeable. They have the same meaning, which means I can make substitutions. So, okay, let's try and use first principles to find the gradient of this curve, this y equals x squared. It looks something like this. It's a parabola on a graph, okay? So what do I need? Well, I need f of x. Well, I've got f of x, okay? But I also need f of x plus h. So if f of x is equal to x squared, then f of x plus h simply means whenever I see an x, I just have to replace it with x plus h. So it's going to be x plus h all squared. That's f of x plus h. Then it's just a case of simply plugging into this formula. So dy by dx is equal to the limit as h approaches 0. I'm just simply using this formula up here, not done anything else. That's equal to, well, on the denominator, I've gone h. On the numerator, I've got f of x plus h, which is x plus h all squared, minus my f of x, which is x squared. Okay, so now it's just a case of playing around with this. Well, what does x plus h all squared? I can expand that out, right? So x plus h all squared, that's equal to x squared plus 2xh plus h squared when I expand that out. So I can just replace that in. So I've got dy by dx is equal to the limit as h approaches 0 still. Nothing else has changed. I've still got it over h, still got a minus x squared, but now I can replace x plus h all squared with this. So I've got x squared plus 2xh plus h squared. Well, immediately I've got to take away x squared and I've got a positive x squared. So those two things cancel. So what am I left with? Well, I've got a 2xh on the top plus an h squared, but then I'm dividing through by h. Well, whenever I divide through by h, I can just do a bit of cancellation jobby. So that cancels with that and cancels with that. So what am I left with? Well, I'm left with that, effectively. Now, what happens when I take the limit as h approaches 0? Well, when I take the limit as h approaches 0, remember what that's actually saying? I'm saying, well, this distance up here on my graph, this h distance here, is becoming closer and closer together. So in other words, those points are getting closer and closer together. They're getting closer and closer together until they're infinitesimally close, that they're behaving like they're at that point, okay? So if they behave, so when I take the limit as h approaches 0, it's behaving as if h is basically 0. So are you happy? That's just going to go to 0. It's going to behave. It's going to be such a small number that's going to behave like it's at 0. So what am I going to be left with? I'm just going to be left with 2x. So what have I said? Well, I started with y equals x squared, right? And then I differentiated to get dy by dx equals 2x. Now I use that word differentiate. This is called the process when I take y and I find the gradient of it, then that's called differentiation. Differentiation. The reason why it's called differentiation is because I'm looking at the change. I'm looking at the difference in x values and y, or y values and x values. dy by dx, change in y over change in x. I'm looking at the change or the difference. So it's called differentiation, okay? Now, this thing on the right-hand side is called the derivative, okay? So let me just say that again. When I take y and I find the gradient of it, so I take y and I find dy by dx, right? That's called differentiation. And the thing which I get, so when I differentiate, the thing which I get, that's called the derivative. Now, there's a few ways that I can write dy by dx. In other words, there's a few ways that I can actually write the derivative, okay? I can either write it as dy by dx, I can also write it, if you remember we had y is equal to f of x, okay, that means that when I differentiate it, so dy by dx, I can also write it as f dash x, okay, that's sometimes, this dash sometimes means the derivative, so I've taken f of x and I've differentiated it to f dash x, okay, but I can also use the y version, so I can also write it as y dash, okay, so the dash just simply means that I differentiate it. This is actually said y prime, okay, and this is sometimes called f prime. Y dash, f dash, same thing, but dy by dx, f dash x, or y dash. They're all the same thing, they all mean the derivative. Now, of course, in reality, wouldn't it be nice if we didn't have to go through all this method of differentiating by first principles and plugging it in formula? It's not too bad, but for difficult functions or for long functions, it can get really, really awkward really quickly. So there's actually a general rule that we can follow, and I'm going to prove that rule in the next video. But essentially, I'm just going to show it here now. If you've got a polynomial, so poly means many, and nomial, well, nomial means named things, but in this context, it just means a term, okay? So if you've got a polynomial, so a polynomial, we've got y is some function of x, and let's suppose that function, okay, a polynomial function, is basically we take the x values, okay, we take x values, and we add lots of x's together. We add lots of x's together. Just move over a little bit. We add lots of x's together. And essentially, we look at the powers of x, we start at 0, and we just increase them by 1. So we go from 0, 1, 2, 3, and we can carry on forever and ever and ever, okay? And then, of course, we can just have coefficients out the front of it, so we can have like a, they're just numbers, a, b, c, d, e, f, so just general numbers. It could be like 3, 4, 5, whatever. So if we do a little bit of simplification, we've got x to the power of 0 is just 1, so it's just a times 1, it's just a, okay? We never normally write b times x to the 1, we just normally write it as bx, because x to the power of 1 or anything to the power of 1 is just itself, right? And then we've got cx squared plus dx cubed, and then we can carry on going. So this is what a polynomial looks like. So if you've got a polynomial, all we have to do is just look at each term and differentiate it. And the general rule is, okay, if you look at each term, we're going to have some number out the front, and then we're going to have an x to the power of some power, right? And then all we have to do is when we differentiate it, the derivative is going to be equal to, well, the power climbs down out the front. So the a just comes along for the ride. The power climbs down, so the n comes down, so the power that comes down. Then we've got x, and then we reduce the power by 1. Okay, reduce the power by 1. So think about differentiation, it's getting less. Okay, it's getting smaller. So power climbs down, and the power reduces by 1. So let me just show you a few examples. And also we look at each term individually. So we look at each term and we do this to every single term. Okay, so let me just give you a few examples. So let's suppose we have y is equal to x squared. Well, we know that this should be equal to 2x, but let's just check to make sure our little rule works. So the power climbs down, so the 2 comes out, then we just reduce that power by 1. So what's 2 minus 1? Well, that's 1, okay, and anything to the power of 1, it's just itself. Right? Well, so it works. You know, we got the same thing out. So what about y equals 3x to the power of 4? So the power climbs down. Okay, the 3 comes along for the ride. The power comes down. Okay, so the 4 comes down, so it's times 4. And then we got x to the power of 4 minus 1. So reduce the power by 1, and that becomes 3. So what's 3 times 4? That's 12. So it's 12x cubed. Okay, what about y is equal to 6? Just a number. Well, if you think about it, when we're finding the gradient of a function, we're looking at the gradient. So y equals 6 just corresponds to a straight line, right? So what's the gradient of that function? It should be 0. But does our rule work? Well, it does if you think about it as 6x to the power of 0, like we did in our polynomial, right? So this is 6x to the power of 0, because x to the power of 0 is just 1, so it's 6 times 1. Power climbs down at the front when we differentiate. So it's 6 times 0, x to the power of minus 1. What's anything times 0 is just 0. So whenever we differentiate a constant, it's just 0. So whenever we just differentiate a number, it becomes 0. Okay, what about y is equal to 3x cubed plus 7x squared plus 5x plus 12? Well, I'm going to actually rewrite this slightly. I'm going to leave the 3x cubed alone and the 7x squared alone. I'm going to write the 5x as 5x to the power of 1. Okay, and I'm going to write the 12 as x to the power of 0. So I'm going to differentiate it. So I'm going to differentiate it down here. So dy by dx. That's going to be equal to, well, I just treat it term by term. So I look at this first term. So it's 3 times 3, which is 27. X, reduce the power by 1, so that becomes 2. Then I look at the next term. So it's going to be 2 times 7. Well, that's 14. X to the power of, well, what's 2 minus 1? That's just 1, so I'm just going to leave it as just x, okay? Then I look at the next term. Power climbs down, so it's 5 times 1, which is 5. And then x to the power of 0. Well, what's x to the power of 0? That's just 1, so it's just 5. Okay, and then let's look at this last term. It's 12, x to the power of 0. The 0 climbs down, so it's 0 times, well, 0 times anything is just 0. So we don't tend to write that. So we're going to differentiate it. Power climbs down and reduce the power by 1. Easy.